Hello everyone, welcome to the SQRT channel. In this video I'm going to talk about 5 problems from the 2022 Canadian Open Mathematics Challenge. Let's get started. For the first problem, we have John had a box of candies. On the first day he ate exactly half of the candies and gave one to his little sister. On the second day he ate exactly half of the remaining candies and gave one to his sister. On the third day, he ate exactly half of the remaining candies and gave one to his little sister, at which point no candies remained. Now the question is how many candies were in the box at the start. Let's see how we are going to solve this problem. But first, think about it and see if you get it right. To solve this problem, I'm going to start from the third day. Let's assume that John had X candies and now he needs to exactly eat half of these, which is basically X over 2, and then give one to his little sister. So X, which the number of candies that we had at the beginning of the third day, should be exactly the same as X over 2 plus 1, because it says that we have no candies by the end of the day 3. Now if we assume that X over 2 plus 1 is X, then X is going to be 2. So basically at the beginning of day 3, John has 2 candies. Now we are going to go to the second day. On the second day, again, let's assume that John already has Y candies. Now he needs to eat exactly Y over 2 and then give one to the sister. So we will have Y over 2 plus 1. But we know that after eating and giving the candies that we are talking about, he's going to have 2 candies. So this time I'm going to say that Y over 2 minus 1 is going to be 2. Y over 2 is basically the number of candies that we are going to have after eating half of it, and then we have this minus 1 because we need to give 1 to the sister. Y over 2 minus 1 is 2, so Y is going to be 6. Now let's go back to the first day. For the first day we are going to do exactly the same thing. Here let's assume that at the beginning of day 1, John has Z candies. So he's going to eat Z over 2 and then give 1 to the sister. So we are going to have Z over 2 plus 1. And if we just want to see how many candies we are going to have after doing all these, it's going to be Z over 2 minus 1. And remember, we calculated that at the beginning of day 2 we had 6 candies, so Z over 2 minus 1 is going to be 6, and Z is going to be 2 times 6 plus 1, which is basically 14. So based on the calculation that we have, Z, or the number of candies that John has at the beginning of day 1, is going to be 14. Now let's see if it is correct. So we have 14. He's going to eat half of it, which is basically 7, and then give 1 to the sisters. So at the end, John has 14 minus 7 minus 1, or 6. Now John is going to eat another half of it. So basically, he's going to eat 3 and then give 1 to the sister. So at the end, we will have 6 minus 3 minus 1, or 2. Now at day 3, John is going to eat half of it, which is basically 1, and then give another 1 to the sister, so he's not going to have anything else. And we see that everything is correct now. Now let's move to the problem number 2. In this problem, we defined a number as palindrome. It belongs to the whole number, and the digits are the same when you read from left to right or right to left. So for example, here we have 565, and you can basically read it from both sides, left to right or right to left, and you're going to end up with the same number. Same thing for 7,887. Now it's asked to find the smallest 6 digit with this property that is also divisible by 12. Let's see how we are going to solve it. So first of all, let's assume that we have a 6-digit number as A, B, C, D, E, F. Now remember, we need to be able to read it from left to right and right to left similarly. So I'm going to replace F with A, E with B, and then D with C. So at the end, I have ABC, CBA as the 6-digit number that I'm interested in. However, it asks to find the smallest 6-digit number that is also divisible by 12. Remember, a number is divisible by 12 if it's divisible by 3 and also by 4. And we know that 3 and 4 are coprime. Now let's focus on these two new things that we have. So we need to find the smallest 6-digit number that is divisible by 3 and 4, and this smallest 6-digit number has the property that we already captured. In particular, we are interested in divisibility by 3. Remember, to find if a number is divisible by 3, we just need to add its digits. Now I'm going to do that. We have 2a, 2b, and 2c. So we need to find a, b, and c in such a way that 2a plus 2b plus 2c is going to be divisible by 3. On the other hand, remember, to find that if a number is divisible by 4, we are interested in the last 2 digits of this number. So here we need to see that if BA as a 2-digit number, or in other words 10 times B plus A, is divisible by 4. And it's easy to verify that we can replace 10 with 2 mod 4. In that case, we are interested to see if we can find any number in such a way that 2b plus a is divisible by 4 and 2b plus 2a plus 2c is divisible by 3. Now let's go back to another fact that we know from the problem. We are interested in the smallest 6-digit number. Now we define the 6-digit number as ABC, CBA. Obviously A cannot be 0, because if so, then the number is not going to be 6-digit, it's going to be 5-digit. So I'm interested in A equals to 1 because it's going to lead to the smallest 6-digit number if I do so. Now A is 1. We are interested in 2b plus A divisible by 4. If A is 1, you cannot find any integer number that 2b plus 1 is going to be divisible by 4. So it's not going to happen. I need to increase the value that I have for A. I increase that to 2. Now let's focus on 2. So I have A equals to 2, and then 2b plus 2 needs to be divisible by 4. Obviously, I'm interested in the smallest 6-digit number. So I'm interested in starting with b equals to 0. Let's use b0. If I do b0, then 2b is going to be 0, and then 2b plus a is going to be just 2, which is not divisible by 4. So I need to increase b to 1. b equals to 1, a equals to 2. I can verify that 2b plus a is basically divisible by 4. And also 2a plus 2b is going to be 6. So I don't need anything for c, because 2a plus 2b plus 2c for c equals to 0 is going to be divisible by 3. So I found my numbers. A needs to be 2, b needs to be 1, and c needs to be 0. So the smallest 6-digit number that I have is 210012, and that concludes the solution. Now let's focus on problem number 3. In this problem, the problem says initially there are 4 red balls, 7 green balls, 8 blue balls, 10 white balls, and 11 black balls on a table. Every minute, we may repaint one of the balls into any of the other 4 colors. Since we have 5 colors, we are going to pick one of the balls. Whatever color it has, we are going to just ignore that and then paint it to one of the other 4 colors that we have on the table. It's going to take us 1 minute. Now the problem is asking what is the number of minutes in terms of minimum number of minutes that we need, after which the number of balls of each of the 5 colors is the same. Let's see how we are going to solve it now. To solve this problem, let me use R for red, G for green, B for blue, W for white, and K for black, because I already had B for blue. Now I have 4R, 7G, 8B, 10W, and finally 11K. In total, I have 40 balls. If you count them, or if you add them together, you're going to end up with 40. I have also 5 different colors, and I'm interested to have the same number of balls per color. So in general, I'm going to have 8 red balls, 8 green balls, 8 blue balls, and so on, so forth. So let's assume that I'm going to do this. Now I have 4 red, so I'm short 4 reds. I have 7 green, so I'm short 1 green. I have 8 blue, which is perfect. I have 10 white, which has 2 extra color, and I have 11 blacks, which means I have 3 extra black balls. Now I need to select one of these balls, the ones that are obviously extra, because for short ones it doesn't make sense to paint them in a different color. So I need to focus on the ones that are extra. How many extra balls do I have? I have 2 white balls and 3 black balls. So 2 plus 3 is going to be 5. So I have 5 extra balls to paint. Each ball is going to take a minute. So I need 5 more minutes, or 5 minutes, to paint these 5 balls into the colors that I'm interested. For example, I can start with painting the 2 white ones as red, and then another 2 black ones as red, and then 1 remaining black one as green, and then I'm done. So I need 5 minutes to do what the problem is asking. For problem number 4, we have a geometry problem. We have 2 parallel lines and we have a triangle ABC. We have a few of these angles given. We have 73, 17, and 13, as you can see here. We also have AC equals to 5 centimeter, and we are interested to find the length of AB in centimeter. Let's see how we are going to solve this problem. To solve this, I'm going to start with some preliminary geometry facts that we can use. So basically, we have the angle that we have in this triangle for C as 90 degrees, because I can say 180 minus 73 minus 17 is basically 90. We know that these 2 lines are parallel, so I can use 73 and then reduce the 13 that I have here, and then find the angle that I have for A in this triangle as 60. So basically now I have a triangle, and this triangle is 90, 60, 30 triangle. And remember, the side that is in front of the 30-degree angle is going to be half of the side that we have in front of the 90-degree angle. The reason is you can just verify that by using sine and cosine formula. So in this case, I'm going to end up with x equals to 2 times 5, which is basically 10, and that concludes the solution. Now we have problem number B1, which is basically problem number 5 of the competition. The competition actually has several parts. We covered the part A, and now we are moving towards part B. In part B, we have this floor function that is defined for any real number, and it's going to generate an integer number. And we know that the value that we have, so let's say that A is here is a real number. So the floor of A is going to be less than or equal to A, and it's going to be greater than A minus 1, which is something that we already know. So the problem is asking what's the difference between the largest integer solution of the equation floor of x over 3 equals to 102 and the smallest integer solution of the equation floor of x over 3 equals to negative 102. Let's see how we are going to solve this. So I'm going to start with saying that I have floor of x over 3 equals to 102. So x over 3 is going to be greater than or equal to 102 and less than 103. Multiplying both sides by 3 leads to x is going to be between 306 and 309, and it can be 306 too. So now the largest integer that I can have is obviously 308. I cannot go beyond that. Now moving to the second one, we have floor of x over 3 equals to negative 102. So x is going to be greater than or equal to negative 306 and less than negative 303. So now in this case, the smallest integer value is going to be exactly negative 306. Now the difference between the largest int and the smallest int is going to be 308 minus 306 or 614, and that's the final answer. Thanks for watching the video. If you would like to see more puzzles, math involved activities, and problems from different math competitions, please subscribe to this channel. Make sure that you watch the other videos that we have, and I hope to see you in the next